A pleasant day to each and everyone. I am Redeemtor Sacayan, a faculty of the Math Department and one of the 2020 College-Bound Program Math instructors. In this video presentation, we will be focusing on the topic Operations with Radical Expressions. Specifically, we will be focusing on the following topics: review on simplifying radicals, adding and subtracting radicals, multiplying and dividing radicals with the same index, multiplying and dividing radicals with different indices, and lastly, rationalizing denominators. To start with, let us recall some important definitions and laws on radicals before discussing the operations with radical expressions. First, let us define what are radicals. So radicals, expressed by the notation nth root of b, are used to denote roots. The number b of the expression is called the radicand, the symbol given is called the radical sign, and the positive integer n is called the index of the radical. Some examples of radicals are the following. First, we have the square root of 3 with index 2 and radicand 3. And for our second example, we have the cube root of 4 with index 3 and radicand 4. Second is the definition of nth root of b, which states that if n is a positive integer and b is a real number such that b raised to the power of 1 over n is a real number, then the nth root of b can be expressed as b raised to the power of 1 over n. To illustrate the above definition, we have the following examples. The cube root of b squared can be expressed as b raised to the power of 2/3. Another one is the fifth root of m cubed, which can also be expressed as m raised to the power of 3/5. Third is the definition of nth root of b quantity raised to the power of n, which states that for all positive integers n, all integers m, and all real numbers b, such that the nth root of b is a real number, then the nth root of b quantity raised to the power of m can be expressed as nth root of b raised to the power of m, which can also be expressed as b raised to the power of m over n. From the above definition, the expression of nth root of b quantity raised to the power of m can be written as exponential expressions such as b raised to the power of m over n. Also, we observe that the index n of the radical is used as the denominator of the power of the radicand, and the exponent m as the numerator of the power of the radicand. For example, the square root of 2ab quantity raised to the power of 3 can be expressed as 2ab quantity raised to the power of 3/2. Last definition that we have to familiarize is the definition of nth root of b raised to the power of n. Consider the following cases. For case 1, if n is an even natural number and b is a real number, then the nth root of b raised to the power of n is just equal to the absolute value of b. For case 2, if n is an odd number and b is a real number, then the nth root of b raised to the power of n is just equal to b. To illustrate the above definition, we have the following examples. First, we have the square root of 4z squared, and we can simplify this by rewriting the expression as the power of the index. Then we obtain 2 times the absolute value of z. Similarly, we have cube root of 8a cubed, and we can simplify this using the same process in example 1. Then we obtain 2a. Because radicals are defined in terms of rational powers, the following properties of radicals are just similar to those of the exponential expressions. If m and n are natural numbers and a and b are positive real numbers, then the product of nth root of A and nth root of B is just equal to nth root of AB. To illustrate the product property of the radical, we have the following example. The product of cube root of 5 and cube root of 2 is just equal to the cube root of 10. Another property of the radical is the quotient property, which states that the nth root of A over the nth root of B can be expressed as the nth root of A over B. To illustrate the quotient property, we have the following example. The cube root of 2 over the cube root of 4 can be expressed as the cube root of 1/2. The last property of the radical is the index property, which states that the nth root of the nth root of A is just equal to the product of m and nth root of A. To illustrate the index property, we have the following example. The square root of the cube root of 2 can be expressed as the sixth root of 2. Now that we have reviewed some important definitions and laws of radicals, we are now ready to perform operations involving radical expressions. First operation is adding and subtracting radicals. So radical expressions can be combined. Either you add or subtract if they are similar or like radicals. So when we say similar or like radicals, these are radical expressions having the same index and the same radicand. For instance, the cube root of 2x and negative 3 cube root of 2x are like radicals since they have the same index 3 and radicand 2x. Combining the two radical expressions, we obtain negative 2 cube root of 2x. From the above example, we observe that combining like radicals is similar to that of adding or subtracting like terms in a polynomial by treating the radical factors as the literal coefficients. That is, a nth root of m plus or minus b nth root of m can be expressed as quantity a plus or minus b times the nth root of m. Sometimes, it is possible to combine radical expressions that do not appear to be like or similar radicals by first simplifying each radical expression. Let us perform the following operation and simplify each answer. Assume that the variable represents a positive real number. The first example, we have 4 cube root of 16 minus 10 cube root of 2. Our second example is 2 sixth root of negative 8 minus 2 cube root of 2 plus 2 cube root of 16. To solve our first example, we only need to simplify the first expression, 4 cube root of 16, since the second expression, 10 cube root of 2, is already in its simplest form. That is, we factor out or express 16 as 2 raised to the power of 4. Second step, we need to group factors such that it can be written as a power of the index. That is, the cube root of 2 to the 4 can be expressed as cube root of 2 to the 3 times 2. Third step, we use the product property of the radicals. Using the product property, the cube root of 2 to the 3 times 2 is just equal to the product of cube root of 2 to the 3 and cube root of 2. Then, by using the definition of nth root of b raised to the power of n, the cube root of 2 to the 3 is just equal to 2. Next is to multiply the numerical coefficient 4 times 2, which is equal to 8. Hence, we can now combine the two radical expressions since they have the same index 3 and the same radicand 2. Now, we compute the difference of the radical coefficients 8 minus 10. Then the whole expression 4 cube root of 16 minus 10 cube root of 2 is just equal to negative 2 cube root of 2. Now we have another example. 2 times 6th root of negative 8 minus 2 times cube root of 2 plus 2 times cube root of 16. From the given expression, we can observe that the first radical expression, 2 times 6th root of negative 8, has different index. But we can still simplify this expression using the index property of the radicals, while the second expression, 2 cube root of 2, is already in its simplest form. And the third expression, 2 cube root of 16, can be simplified by factoring 16. To solve our second example, first step, we use the index property of the radical. So we can write the first term, 6th root of negative 8, as the square root of the cube root of negative 8, or the cube root of the square root of negative 8. However, it is more appropriate, or we prefer to choose the first expression, the square root of the cube root of negative 8, since negative 8 is a perfect cube number and it can be expressed as the power of the index. And to simplify the third term, 2 cube root of 16, we factor out 16 by 8 times 2 and express 8 as the power of the index, which is 2 to the power of 3. Third step, we can simplify the first and third expression using the definition of nth root of b raised to the power of n. Next is using the definition of the square root of negative numbers. Then we can simplify the square root of negative 2 to I square root of 2. On the other hand, we multiply the numerical coefficient 2 times 2, so we have 4. And since the second expression, 2 cube root of 2, and the third expression, 4 cube root of 2, have the same index and the same radicand, then we can just combine the two expressions by adding the radical coefficients, obtaining 6 cube root of 2. Another operations we can perform involving radical expressions are multiplying and dividing radicals with the same index. Below are 3 examples, and to perform each operation, we can simplify radical expressions using the product property and quotient property of the radicals and using the distributive property of real numbers. In our first example, we are going to multiply the two radical expressions. Using the product property of the radicals, the product of 4th root of 8 and 4th root of 4 can be written as one radical expression. So we have 4th root of the product of 8 and 4. The next step, we group the factors so that it can be written as the power of the index. Finally, using the definition of nth root of b raised to the power of n, the 4th root of 2 raised to the power of 4 is just equal to 2. Then the product of 4th root of 8 and 4th root of 4 is just equal to 2 4th root of 2. For our second example, we are going to divide radicals. To solve this, we use the quotient property of the radical. So the square root of 21x raised to the power of 7 y squared z to the power of 9 over the square root of 3x squared y squared z can be expressed as the square root of 21x raised to the power of 7 y squared z to the 9 over 3x squared y squared z. Next, we cancel out like terms in the numerator and denominator of the radical, obtaining square root of 7 x to the 5th z to the 8th. Then we group factors to write the radical expression as the power of the index, that is the square root of x raised to the power of 4 z raised to the power of 8 times 7x is just equal to the square root of the quantity x squared z to the 4 quantity raised to the power of 2 times 7x. Next, using the definition of nth root of b raised to the power of n, we factor out x squared z raised to the power of 4 from the square root of the quantity x squared z to the 4 quantity squared times 7x. So we get x squared z to the 4 times the square root of 7x. Then we have our third example, negative square root of 3 times the quantity 2 square root of 3 minus 4 square root of 2. In order to simplify the given radical expression, we will be using the distributive property of real numbers and the product property of the radicals. First step, by distributive property of the real numbers, we will distribute negative square root of 3 to each term, 2 square root of 3 and negative 4 square root of 2. So we have negative square root of 3 times 2 square root of 3 plus the square root of 3 times 4 square root of 2. Second step, we use the product property of the radical. So negative square root of 3 times 2 square root of 3 is just equal to negative 2 square root of 9, and the square root of 3 times 4 square root of 2 is just equal to 4 square root of 6. Next step, we have negative 2 square root of 9, which is just equal to negative 2 times 3, since the square root of 9 is just 3. And adding it to 4 square root of 6, we obtain negative 6 plus 4 square root of 6. Another operations involving radical expressions are multiplying and dividing radicals with different indices. Below are few examples. First, we have the product of cube root of x and fourth root of 2x. And the second one, we have the square root of xy over the fourth root of 16xy. And to perform each operation, we have to be guided by the following steps. First, express the radicals as term with fractional exponents. Second, write the fractional exponents in the equivalent form using the LCM or the least common multiple of all denominators as common denominator. Third, rewrite the expressions as radicals with this LCM as the common index. The numerator of each fractional exponent becomes the exponent of the corresponding radicand. And fourth, perform the indicated operations, then simplify the expression obtained. First example, we have the product of cube root of x and fourth root of 2x. To solve this, first step, we rewrite the radicals as rational exponents. That is, the cube root of x times the fourth root of 2x can be expressed as x raised to the power of 1/3 times 2x quantity raised to the power of 1/4. Second step, we write the exponents in their equivalent form using the LCM. So the LCM of 3 and 4 is 12. So we have x raised to the power of 4 over 12 times 2x quantity raised to the power of 3 over 12. Third step, we rewrite the expression in radical notation using the product rule or the product property of the radicals. So we have the 12 root of x raised to the power of 4 times 2x quantity raised to the power of 3. Next step is to simplify the radicals. Then the 12 root of x raised to the power of 4 times 2x quantity raised to the power of 3 is just equal to the 12 root of 8x raised to the power of 7. Since 2 to the 3 is 8, and the product of x raised to the power of 4 and x raised to the power of 3 is just x raised to the power of 7. For our second example, we have square root of xy over the fourth root of 16xy. And to solve this, just like what we did in the previous example, we rewrite first the radicals as rational exponents. That is, the square root of xy over the fourth root of 16xy can be written as xy quantity raised to the power of 1/2 over 16xy quantity raised to the power of 1/4. Second step, we write the exponents in the equivalent form using the LCM or the least common multiple. So the LCM of 2 and 4 is just 4. Then we have xy quantity raised to the power of 2 over 4 over 16xy quantity raised to the power of 1/4. Third step, we rewrite the expression in radical notation using the quotient property of the radicals. So we have 4th root of xy quantity squared over 16xy. Fourth step, we cancel like terms or similar terms in the numerator and denominator of the radical expression, obtaining 4th root of the quantity xy over 16. Then using the quotient property of the radicals, we write the radical expression 4th root of the quantity xy over 16 as 4th root of xy over the 4th root of 16. After that, we group factors to express 16 as the power of the index. That is, the 4th root of 16 can be written or can be expressed as the 4th root of 2 raised to the power of 4. Finally, using the definition of the nth root of b raised to the power of n, the 4th root of xy over the 4th root of 2 raised to the power of 4 is just equal to the 4th root of xy over 2. Now we are down with our last topic, rationalizing denominators. So this refers to any process of rewriting the given fraction so that the denominator contains only rational expressions. So the following are techniques or some techniques for rationalizing denominators. First, to rationalize a denominator of the form a minus b square root of m or a plus b square root of m, multiply both the numerator and denominator by a conjugate. So to illustrate what is a conjugate, suppose we have the expression a plus b square root of m, then its conjugate is a minus b square root of m, or vice versa. Second, if a is equal to 0, from the expression a plus or minus b square root of m, then the rationalizing factor for the square root of m is itself. The third, for cube roots, choose a rationalizing factor that generates a perfect cube. Now we have 7 examples, and to perform each operation, we just need to remember the techniques for rationalizing denominators. First, rationalize the denominator of 6 over square root of 2. So in this problem, we simply look for a suitable multiplier to the entire fraction that will remove both the index and radical symbol from the denominator. So in our example, the desired multiplier is square root of 2 over the square root of 2. The next step, we multiply the expression 6 over square root of 2 with our desired multiplier square root of 2 over square root of 2. So we have 6 square root of 2 over the square root of 2 quantity squared. Then simplify the expression using the definition of nth root of b raised to the power of n. So 6 square root of 2 over square root of 2 quantity squared is just equal to 6 square root of 2 over 2. Then we divide the radical coefficient 6 by 2. We obtain 3 square root of 2. So the whole expression 6 over the square root of 2 is just equal to 3 times the square root of 2. For our second example, rationalize the denominator of square root of 3 over 2 square root of 3. So just like in our previous example, we are going to look for a suitable multiplier. and that is the square root of 3 over the square root of 3. Then we multiply 3 over 2 square root of 3 by our multiplier, the square root of 3 over the square root of 3. So we obtain 3 square root of 3 over 2 times 3, since the square root of 3 times the square root of 3 is just 3. Then we cancel out 3 both in the numerator and denominator, so we have square root of 3 over 2. Now we have our third example, negative 3 over the cube root of 4. In order to rationalize this problem, we are going to look for the multiplier or the rationalizing factor that will generate a perfect cube in the denominator. If you can observe in the denominator, the only possible rationalizing factor that would generate a perfect cube would be the cube root of 2. Then, using the product property of the radicals, we multiply negative 3 over the cube root of 4 by our multiplier, which is the cube root of 2 over the cube root of 2. We obtain negative 3 cube root of 2 over the cube root of 2 raised to the power of 3. Then, simplifying the expression using the definition of nth root of b raised to the power of n, the expression in the denominator, cube root of 2 raised to the power of 3, is just 2. Then we have our third example, the cube root of the quantity 2 over 3 x raised to the power of 4. Now, to rationalize this expression, first we use the quotient property of the radicals. That is, the cube root of the quantity 2 over 3 x raised to the power of 4 can be written as the cube root of 2 over the cube root of 3 x raised to the power of 4. Then, using the same technique in our second example, we are going to look for a rationalizing factor that will generate a perfect cube in the denominator. So the desired multiplier would be the cube root of 9x squared over the cube root of 9 squared, which can be expressed as the cube root of 3 squared x squared. Then, using the product property of the radicals, we multiply the expression cube root of 2 over the cube root of 3x raised to the power of 4 by our multiplier, which is the cube root of 3 squared x squared over the cube root of 3 squared x squared. We obtain the cube root of 18x squared over the cube root of 27x raised to the power of 6. Then, we can rewrite the expression in the denominator, the cube root of 27 x raised to the power of 6 as the power of the index. So we have the cube root of 3x squared quantity cube. Lastly, using the definition of nth root of b raised to the power of n in the denominator, we factor out 3x squared. So the whole expression, the cube root of 2 over 3x raised to the power of 4 is just equal to the cube root of 18 squared over 3x squared. For our fourth example, we are going to rationalize the expression a raised to the power of negative 3 over 5. First, using the laws of exponent, we can write a raised to the power of negative 3 over 5 as 1 over a cube quantity raised to the power of 1/5. Second step, we rewrite the expression in radical notation. So 1 over a cube quantity raised to the power of 1/5 is just equal to 1 over the 5th root of a cube. Third step, we rationalize the denominator by looking for a multiplier that will remove both the index and radical symbol. So in this case, our desired multiplier, both in the numerator and denominator, is the 5th root of a squared. Fourth step, we use the product property of the radicals in multiplying 1 over the fifth root of a cubed with our desired multiplier, or the rationalizing factor. So we get the fifth root of a squared over the fifth root of a raised to the power of 5. After that, we use the definition of nth root of b raised to the power of n. So the expression in the denominator, the fifth root of a raised to the power of 5, is just equal to a. So the expression, or the whole expression, a raised to the power of 3 over 5 is just equal to the fifth root of a squared over a. Now, we are down with our second to the last example in rationalizing denominators. So we have 3rs quantity raised to the power of 3 halves, or negative 3 halves, and the solution for this problem is just similar with our previous example. First, we rewrite the expression in radical notation. Thus, the 3rs quantity raised to the power of negative 3 halves can be written as 1 of the square root of 3rs quantity cubed. Next step, we simplify the radical expression of the denominator by factoring out 3rs. So we have 1 over 3rs times the square root of 3rs. Then we look for the rationalizing factor to remove the index and the radical symbol in the denominator. Using the second technique of rationalizing denominator, the multiplier both in the numerator and denominator would be the square root of 3rs. Using the product property of the radicals, we multiply 1 over 3rs square root of 3rs with our multiplier, or rationalizing factor. Then we get the square root of 3rs in the numerator, and in the denominator we obtain 3rs quantity square root of 3rs quantity squared. Then simplify the expression, the square root of 3rs quantity squared in the denominator, by using the definition of nth root of b raised to the power of n. So we get 3rs. Next step, we multiply the expression in the denominator. So the square root of 3rs over 3rs times 3rs is just equal to the square root of 3rs over 9r squared s squared, where r and s must be greater than 0. And we have our last example, 2 over the quantity 3 plus the square root of 7. In order to rationalize the denominator of the given example, first is we multiply both the numerator and denominator by its conjugate. So the conjugate of 3 plus square root of 7 is just 3 minus the square root of 7. In order to multiply the expression, particularly in the denominator, we will use the FOIL method. That is, we multiply the respective first terms, outer terms, inner terms, and last terms. So in the numerator, we have 2 times the quantity 3 minus the square root of 7. And in the denominator, we have 3 times 3 plus 3 times negative square root of 7 plus the square root of 7 times 3 minus the square root of 7 times the square root of 7. Next step, we simplify the expression by adding the product of each term in the denominator. Then we obtain 2 times the quantity 3 minus the square root of 7 in the numerator, and we have 9 minus 7 in the denominator. Since 9 minus 7 is just 2, then we cancel out 2 both in the numerator and denominator. So we get 3 minus the square root of 7.